twilight zone of military aviation exists in a realm where physics meets extreme engineering, a place where the air itself becomes a solid wall and friction turns metal into liquid plasma. For decades, the global strategic balance has been dictated not just by who has the biggest arsenal, but by who can see, react, and strike the fastest. When the United States retired the legendary SR-71 Blackbird in the late 1990s, the public was told that an era had ended. The official narrative was simple and seemingly logical. Orbital satellites had advanced to the point where high-altitude, high-speed reconnaissance aircraft were obsolete. Satellites could peer down from space without risking a pilot's life, making the immense cost of maintaining a Mach 3 fleet unjustifiable. But this explanation always carried a fundamental flaw that defense analysts and aerospace historians immediately recognized. Satellites operate on predictable orbital paths. A foreign adversary can calculate exactly when a reconnaissance satellite will pass overhead and simply cover up their secret projects, park their experimental hardware inside hangars, or pause sensitive operations until the eye in the sky has moved past the horizon. True strategic intelligence requires unpredictability. It requires the ability to launch an asset on demand, penetrate contested airspace, gather real-time data, and return home before the adversary even realizes their security has been breached. The retirement of the Blackbird did not signal the end of high-speed atmospheric flight. It merely marked the moment the transition went completely dark, descending into the multi-billion-dollar labyrinth of deeply classified special access programs, colloquially known as black projects. To truly understand the trajectory of this hidden aerospace revolution, one must examine the physical and geopolitical catalysts that forced the military-industrial complex to push past the boundaries of conventional stealth. For the past 30 years, low observable technology, or stealth, was the ultimate trump card. The F-117 Nighthawk, the B-2 Spirit, and later the F-22 and F-35 were designed to evade radar detection by shaping their airframes to reflect radar waves away from the receiver and using radar-absorbent coatings. This strategy worked flawlessly in low to medium intensity conflicts, allowing coalition forces to operate with near impunity. However, stealth is not an invisible cloak, it is a delay mechanism. Advanced adversaries have spent the last 3 decades developing counter-stealth technologies, including low-frequency radars, multi-static radar networks, and highly sensitive infrared search and track systems. In a modern, highly contested anti-access and area denial environment, a slow-moving stealth aircraft is no longer safe. The radar cross-section reduction that once guaranteed survival is being steadily eroded by computational leaps in signal processing. This created a profound dilemma for defense planners. If you can no longer hide completely, how do you survive in the sky? The answer is as brutal as it is simple. You move so fast that even if the enemy sees you, they cannot stop you. This is the core philosophy behind the hypersonic paradigm shift. Speed has become the new stealth. The transition from supersonic flight, which exceeds the speed of sound at Mach 1, to hypersonic flight, which begins at Mach 5 and goes beyond, is not a matter of simply adding a more powerful engine. It represents an entirely different domain of physics. In supersonic flight, the air flows around an aircraft like water around a smooth stone. At hypersonic speeds exceeding 3,800 miles per hour, the air molecules do not have time to smoothly displace. Instead, they slam violently into the leading edges of the aircraft, creating a detached shock wave that compresses the air to extreme pressures and temperatures. The kinetic energy of the vehicle is converted into thermal energy, wrapping the airframe in a superheated shroud of gas that can easily exceed 2,000 degrees Fahrenheit. At these temperatures, conventional aerospace materials like aluminum and titanium lose their structural integrity, softening like butter. The air itself begins to chemically dissociate. Oxygen and nitrogen molecules tear apart, creating a highly reactive plasma field around the vehicle. This plasma can block radio communications, blinding the aircraft's onboard sensors and isolating it from the outside world. To survive in this environment, a black project vehicle must utilize exotic carbon-carbon composites, ceramic matrix materials, and active cooling systems where cryogenic fuel is pumped through the skin of the aircraft to absorb the heat before being fed into the engine. Every flight at these speeds is an exercise in controlled vaporization, where the vehicle is constantly on the verge of melting itself out of existence. The breadcrumbs of this hidden evolutionary leap have slipped into the public eye through a series of anomalous events scattered across the last few decades. In the early 1990s, seismic monitors operated by the United States Geological Survey in Southern California began detecting unique, recurring tremors. These were not the typical rolling waves of an earthquake, nor were they the standard sharp cracks of a conventional sonic boom from a fighter jet. They were recorded as continuous, low-frequency atmospheric pulses that rattled windows across hundreds of miles. Around the same time, aviation observers and photographers began spotting bizarre contrails in the high atmosphere. Unlike the smooth, solid white lines left by commercial airliners, these contrails resembled a string of pearls or a chain of donuts linked together by a thin thread. Analysts hypothesized that these patterns were the visual signature of a highly experimental propulsion system, known as a pulsed detonation wave engine, which operates by detonating fuel-air mixtures at supersonic speeds inside a tube, producing high-frequency thrust pulses. This mysterious aircraft was given the mythical moniker of Aurora, a name that accidentally slipped out in a 1985 federal budget document listed alongside the U-2 and SR-71. While the government adamantly maintained that Aurora was merely a code name for a funding element related to the B-2 bomber, the persistent acoustic and visual anomalies suggested that a high Mach technology demonstrator was already ripping through the upper atmosphere, proving that hypersonic flight was attainable. The urgency to fully transition these experimental platforms into operational, mass-produced reality reached a boiling point due to a radical shift in the global balance of power. For a long time, the West held a monopoly on high-end aerospace technology. That monopoly has dissolved. Competitor nations realized they could not match the massive carrier strike groups or the vast fleets of conventional stealth fighters line for line. Instead, they invested heavily in asymmetric capabilities, specifically hypersonic glide vehicles and anti-ship ballistic missiles designed to deny access to vital maritime corridors. When an adversary possesses a missile that can travel at Mach 7 and maneuver dynamically through the atmosphere, traditional missile defense systems, which are calibrated to track predictable ballistic trajectories, become effectively useless. The realization that foreign powers were successfully weaponizing hypersonics sent shockwaves through the defense establishment. The sky was no longer a sanctuary. The United States found itself in a position where it had to quickly operationalize its own dormant hypersonic research to restore deterrence. The black projects that had spent decades undergoing clandestine testing in the remote corners of the Nevada desert and the Pacific test ranges were suddenly pushed into overdrive. The goal was no longer just to build a fast research plane, but to create a fully integrated, reusable hypersonic platform capable of long-range reconnaissance and rapid precision strike. At the heart of this technological resurrection is the evolution of air-breathing propulsion, specifically the transition from the ramjet to the scramjet, or supersonic combusting ramjet. A conventional jet engine relies on spinning compressor blades to squeeze incoming air before mixing it with fuel and igniting it. However, as an aircraft approaches Mach 3, the incoming air rushes in so fast that the compressor blades become a hindrance, creating massive drag and overheating. A ramjet solves this by removing the moving parts entirely, relying on the high forward speed of the aircraft to naturally compress, or ram, the air into the engine casing. But there is a catch. A traditional ramjet must slow the incoming air down to subsonic speeds inside the combustion chamber for the fuel to ignite properly. When you try to fly faster than Mach 5, slowing that air down generates so much heat and pressure that the engine melts internally. This is where the scramjet comes in. In a scramjet engine, the air flows through the entire propulsion system at supersonic speeds. Igniting fuel in a supersonic airstream is frequently compared to trying to light a match inside a Category 5 hurricane and keeping it burning. If the fuel does not mix and ignite within a fraction of a millisecond, the engine experiences a flameout, losing all thrust instantly. The geometry of the engine must be mathematically perfect, using the shock waves generated by the vehicle's nose to compress the air precisely before it enters the combustion chamber. This requires an advanced integration of aerodynamic design known as a wave rider, where the entire fuselage of the aircraft is sculpted to ride on top of the very shock wave it creates, using that high-pressure wave to generate lift and feed the underslung scramjet engines. The physical architecture of such an aircraft looks entirely alien compared to conventional aviation. There are no vertical tail fins, no protruding cockpit windows, and no sharp right angles. The vehicle is a highly blended, flattened wedge designed to minimize drag and manage the extreme thermal loads. The cockpit, if it even accommodates a human pilot, is entirely enclosed, relying on synthetic vision systems and external sensor arrays to project a digital representation of the world onto the pilot's helmet or display screens. At Mach 6, a human being cannot react fast enough to manual flight controls to correct an aerodynamic instability. A single millimeter of overcorrection could cause the airframe to lift too high, catch the hypersonic airflow, and instantly disintegrate into a ball of debris. Therefore, the flight control systems must be governed by highly autonomous, hardened artificial intelligence networks capable of making thousands of micro adjustments per second to flaps and thrusters. The fuel itself cannot be standard aviation kerosene, which degrades under high temperatures. Instead, these platforms often utilize advanced endothermic hydrocarbon fuels or cryogenic hydrogen, which act as both a propellant and a cooling agent, circulating through the structural veins of the aircraft to keep the leading edges from reaching their thermal failure points. The public received a stunning, semi-official glimpse into this hidden world through an unexpected avenue: popular culture. When the production team behind a major Hollywood aviation blockbuster wanted to feature a futuristic, Mach 10 experimental aircraft called the Dark Star, they approached the legendary Advanced Development Division of Lockheed Martin, known as Skunk Works. The engineers at Skunk Works did not just draw up a fantasy concept, they built a full-scale, physically authentic mock-up of a hypersonic aircraft. The design was so detailed, so structurally logical, and so realistic that foreign intelligence agencies reportedly repositioned their spy satellites to monitor the physical prop when it was moved outside onto the tarmac, genuinely believing it was a secret black project prototype being prepped for testing. The line between fiction and reality was intentionally blurred. Shortly after, statements from aerospace executives and high-ranking military officials began to shift in tone. They stopped talking about hypersonics as a distant, futuristic goal for the year 2040 and began discussing it as a mature capability that was already being integrated into the modern order of battle. The acknowledgement of projects like the SR-72 concept confirmed what many had suspected. The successor to the Blackbird was no longer a theoretical drawing on a whiteboard. It was an active participant in the silent war for global atmospheric supremacy. The operational implications of a reusable hypersonic platform completely rewrite the rules of modern geopolitics. If a nation can launch an aircraft that travels at 1 mile per second, the tyranny of distance is effectively conquered. A deployment from a base in the continental United States could reach any target on any continent in under 90 minutes. This compresses the decision-making cycle of an adversary to absolute zero. Traditional early warning systems might detect the launch or the approach, but the sheer velocity of the vehicle leaves no time to scramble interceptors, optimize air defense missile batteries, or move high-value assets into underground bunkers. Furthermore, a hypersonic vehicle operating at altitudes between 80,000 and 150,000 feet sits in the ignorance zone of global defense. It flies too high for conventional surface-to-air missiles, which lose aerodynamic maneuverability in the thin upper atmosphere, yet it flies too low for exo-atmospheric space interceptors designed to target ballistic missiles in orbit. It operates in a sweet spot of absolute vulnerability for the defender. It turns time into a kinetic weapon. The psychological impact of knowing that a strike platform could appear overhead with zero warning creates a powerful deterrent effect, completely shifting the calculus of global crisis management and forcing potential adversaries to reconsider aggressive maneuvers. As we peer deeper into the mechanism of these classified programs, it becomes evident that we are witnessing the dawn of a new age in human transportation, one that mirrors the transition from props to jets in the mid-20th century. The technologies being perfected in the dark, such as advanced thermal protection systems, supersonic combustion, and autonomous high-velocity flight controls, will eventually trickle down into the civilian sector, potentially enabling point-to-point suborbital travel that could connect London to Tokyo in the span of an afternoon. But for now, this technology remains locked away behind guarded perimeters, deep underground facilities, and highly restrictive security clearances. The faint rumblings in the night sky and the unusual contrails fading in the upper atmosphere are the only outward signs of a massive coordinated effort to maintain dominion over the ultimate high ground. The ghost in the Mach is real, and its emergence from the shadows is fundamentally altering the future of human conflict and aerospace engineering forever. The industrial execution of a hypersonic asset shifts the conversation from theoretical physics to the harsh realities of materials science, supply chains, and fiscal endurance. To construct a vehicle capable of routine, reusable operations at Mach 6 and beyond requires an unprecedented synchronization of advanced metallurgy, computational fluid dynamics, and automated manufacturing. In conventional aerospace manufacturing, the assembly line is a known variable. Aluminum sheets are riveted to titanium spares, and standard composite panels are cured in standard autoclaves. Hypersonic manufacturing completely upends this methodology. Every single component of a high Mach airframe must be treated as a thermal management device. The leading edges of the wings, the nose cone, and the interior walls of the propulsion system experience localized thermal loading that would instantly vaporize standard military aerospace materials. To combat this, advanced defense contractors have turned to ceramic matrix composites and ultra-high temperature ceramics. These materials, often consisting of silicon carbide matrices reinforced with carbon fibers, can withstand temperatures exceeding 3,000 degrees Fahrenheit without losing their tensile strength or undergoing catastrophic thermal shock. However, these materials are notoriously difficult to machine and shape. They cannot be stamped out by heavy presses or milled by standard computer numerical control machines. Instead, they require specialized additive manufacturing techniques, such as laser powder bed fusion and robotic fiber placement, where components are grown layer by layer under precise atmospheric conditions. This level of manufacturing complexity introduces a massive bottleneck in production capability. It turns the creation of a single airframe into a bespoke, artisan process that takes months of specialized labor, severely limiting the scalability of the fleet and driving the unit cost of each aircraft into astronomical figures. Beyond the exotic materials forming the outer skin, the true engineering miracle lies beneath the surface in the active thermal protection and fluid management systems. When an aircraft travels at such extreme velocities, the heat radiating from the outer hull threatens to cook the internal avionics, fuel cells, and structural bulkheads. Traditional insulation panels are far too bulky and heavy to be effective within the sleek, aerodynamic constraints of a hypersonic wedge design. The solution implemented in modern black projects is a complex, closed-loop convective cooling network. The aircraft's fuel, typically a highly dense endothermic hydrocarbon or liquefied cryogenic gas, is circulated through a microscopic web of channels embedded directly within the double-walled structure of the leading edges before it ever reaches the combustion chamber. In essence, the aircraft uses its own propellant as a giant heat sink. As the cold fuel absorbs the immense heat from the airframe, a chemical reaction occurs within the fuel itself, a process known as thermal cracking. This cracking breaks down the long-chain hydrocarbon molecules into smaller, highly volatile components like hydrogen and ethylene. This serves a dual purpose. It cools the critical structural points of the aircraft to manageable levels while simultaneously prepping the fuel for the incredibly rapid ignition required inside the Scramjet engine. This symbiotic relationship between structural cooling and propulsion efficiency is the cornerstone of sustainable hypersonic flight, but it introduces a terrifying margin for error. A single microscopic blockage in the cooling channels, a microscopic fracture caused by thermal expansion, or a minor fluctuation in fuel pressure would result in instantaneous structural failure, as the superheated airframe would literally consume itself from the inside out within milliseconds. The logistical footprint required to support such a highly advanced platform is another layer of secrecy that defense analysts must piece together. A hypersonic aircraft cannot simply roll out of a standard hangar at a typical Air Force base, refuel from a standard tanker, and take off on a routine runway. The infrastructure required is immense and highly specialized, because these vehicles often utilize non-standard propellants. Bases like Area 51, the Tonopah Test Range, and the high-altitude test centers in the Pacific must be equipped with massive cryogenic storage facilities, high-pressure gas distribution networks, and specialized hazardous material handling teams. Furthermore, the maintenance cycle of a hypersonic vehicle after a single mission is closer to that of the space shuttle than a traditional fighter jet. Every square inch of the thermal protection system must undergo non-destructive testing using ultrasonic and X-ray scanning technologies to detect internal delamination, microscopic void formations, or structural fatigue within the ceramic composites. The scramjet engines, which lack moving parts but endure extreme vibrational and acoustic stress, must be digitally mapped to ensure that the internal geometry has not shifted by even a fraction of a millimeter due to the intense thermal expansion. This means that for every hour a hypersonic asset spends ripping through the upper atmosphere, it requires hundreds of hours of highly specialized engineering oversight on the ground, effectively restricting its operational frequency and making the concept of a rapid, high-tempo deployment cycle an ongoing engineering challenge. The economic reality of these programs represents a silent warfare fought within the halls of government budgeting and corporate ledgers. The development of a hypersonic platform is a bottomless pit of capital expenditure. It is estimated that the development, testing, and infrastructure creation for a viable, reusable hypersonic reconnaissance and strike asset can easily consume tens of billions of dollars before a single operational mission is flown. In the United States, these funds are obscured within the classified black budget, scattered across various line items under intentionally vague titles like Advanced Aerospace Logistics, Next Generation Sensor Integration, or Prototype Evaluation Services. This financial obfuscation is necessary not only to hide the technological capabilities from foreign adversaries, but also to protect the program from domestic political scrutiny. When a single test flight of an experimental technology demonstrator can cost upwards of $50 million and frequently ends in the vehicle crashing into the ocean due to a minor software glitch or a thermal protection failure, maintaining public and congressional backing is exceptionally difficult. The military-industrial complex must walk a fine line between proving the capability works to maintain funding while keeping the failures locked away in classified briefing rooms. This economic burden creates a natural barrier to entry. Only a handful of nations with massive gross domestic products and highly sophisticated industrial bases can even attempt to compete in this arena, turning the hypersonic race into an exclusive club where the buy-in fee is economic exhaustion. The integration of these platforms into the broader command and control architecture introduces a profound paradigm shift in how intelligence is processed and acted upon. In conventional military operations, the loop of finding a target, fixing its location, tracking its movements, targeting it, executing the strike, and assessing the damage can take hours, if not days. A hypersonic asset collapses this entire sequence into a singular, near-instantaneous event. Operating at altitudes where the atmosphere transitions into the blackness of space, the onboard synthetic aperture radar and hyperspectral imaging suites can map vast swaths of territory through any weather condition, processing the data locally via hardened edge computing systems. This eliminates the latency involved in transmitting massive data files back to ground stations via satellite links, which are vulnerable to electronic jamming and cyber disruption. The aircraft becomes an autonomous intelligence hub, capable of identifying a high-value asset, determining its strategic importance, and utilizing an underslung hypersonic glide weapon to neutralize it within a window of minutes. This level of rapid response completely invalidates traditional defensive postures, which rely on early warning indicators and mobilization timelines. For an adversary, the first indication that they have been targeted is the arrival of the kinetic shockwave itself, creating a state of perpetual vulnerability that fundamentally alters the psychology of modern deterrence. The geopolitical ripple effects of this technological evolution are already reshaping international alliances and military doctrines across the globe. As rumors and semi-official acknowledgments of these black projects become more frequent, rival nations are being forced to completely re-engineer their defensive networks. The massive investment in traditional air defense systems, such as long-range surface-to-air missile batteries and integrated radar grids, is rapidly becoming obsolete. Nations are now pivoting their resources toward the development of directed energy weapons, such as high-power solid-state lasers and high-power microwave systems, as these are the only defensive technologies capable of traveling at the speed of light to intercept a target moving at Mach 6. Additionally, there is a frantic rush to develop space-based tracking layers, constellations of hundreds of low Earth orbit satellites equipped with wide field of view infrared sensors designed to track the unique thermal signatures of hypersonic vehicles as they glide through the upper atmosphere. This has triggered a secondary space race, where the ultimate goal is not the weaponization of orbit, but the creation of an unjammable, real-time tracking blanket that can eliminate the element of surprise that hypersonics rely so heavily upon. The sky is no longer a localized domain. It has become intrinsically linked with space assets, creating an interdependent theater of operations where the line between atmospheric aviation and orbital warfare is permanently blurred. The technological spin-offs from these highly classified aerospace endeavors are poised to eventually revolutionize the civilian world, much like the race to the moon did in the mid-20th century. The breakthroughs in ultra-high temperature materials are already finding applications in commercial power generation, deep-crust geothermal drilling, and advanced manufacturing where components must survive extreme environments. The advancements in autonomous flight control algorithms and synthetic vision systems are paving the way for the next generation of commercial autonomous aircraft and unmanned cargo delivery networks. More profoundly, the perfection of air-breathing scramjet propulsion holds the key to drastically reducing the cost of access to space. By utilizing a hypersonic first-stage aircraft that breathes oxygen from the atmosphere rather than carrying massive, heavy liquid oxygen tanks like a traditional rocket, the aerospace industry can move toward two-stage-to-orbit reusable launch systems. This could allow satellite payloads to be launched from standard runways with the frequency and reliability of commercial cargo flights, democratizing space access and accelerating the orbital economy. The massive capital injected into the dark world of military black projects acts as a high-velocity incubator for the foundational technologies of the 21st century, proving that while these systems are born out of strategic necessity, their ultimate legacy may be the transformation of global human connectivity. The veil of secrecy surrounding these platforms will inevitably continue to thin as operational requirements demand their deployment in real-world scenarios. You cannot utilize a revolutionary capability to deter an adversary if the adversary is completely unaware that the capability exists. The coming years will likely see a calculated, gradual declassification process, where partial capabilities, carefully curated flight footage, and sanitized engineering data are released to the public. This serves to signal strength to global rivals while validating the immense financial expenditures to taxpayers and lawmakers. Until that day comes, the truth remains written in the anomalous data points. The high-altitude sonic booms that shake coastal cities, the unexplained line items in federal budgets, the recruitment drives for specialized engineers skilled in high-temperature materials, and the fleeting geometric silhouettes captured by high-altitude observers. The hypersonic aircraft is no longer an engineering fantasy or a Hollywood prop. It is the silent, lethal apex predator of the modern sky, an invisible pivot around which the future of global strategy, material science, and human engineering now revolves, changing everything we thought we knew about the limits of flight.